Hello. In case I forget to say it later on, as I'm heading off, thank you for hosting me here. It's been a delight to be with you all. I'm going to start fairly promptly today, even while people are streaming in, because at 4 o'clock on the dot, I will need to be going out. My flight is at 6:15, so I'm literally, my bag is there, ready to go to the airport. So today I need to be finishing on time. This is quite a novel thing for me. If you have questions throughout the presentation that you would normally ask me afterwards or whatever, then please feel free to email me afterwards if it's something that you don't want to share with the rest of the room. But do feel free to just shout loudly questions during the session. I will spend quite a lot of the session looking directly at my laptop, so I won't see hands raised politely in the air. Please just shout out. And if I don't stop, shout louder and get your friends to shout as well. Okay. And I'm losing my microphone. There we go. So, this is the agenda. I don't have slides in PowerPoint because I would be switching between PowerPoint and Visual Studio so frequently that it felt like a really bad idea. So this is what we're going to be talking about today. To give a little bit of background, I've been interested in immutability for quite a while, and I found it basically a pain to work with in C#. As a little bit of sort of professional background, back sort of 7 years ago or so, I ported the protocol buffers serialization system to C#, and then I followed the Java pattern of making everything immutable with one of the builder patterns that we'll see later on. When I came to do Proto 3, the later version of it, sort of last year, we decided to go for mutability because it was simply easier from the client's perspective. Despite our best efforts to make it as usable as we couldn't keep immutability with the usability. And this has caused various problems. It's lowered the barrier to entry. There are trade-offs involved, and we'll be talking about some of those. So I have a definite professional interest in this. This is not theoretical, and this is something that you should be thinking about often. Okay, let's start off talking about what kinds of immutability there are. So it's not, it's not just a yes or no, is this immutable? There's a whole spectrum. Now, before I start going any further, how many of you have done any Java? Okay. Someone shout out a Java class that's immutable. String. Everyone agree that Java string is immutable? Okay, we'll come back to it. Right. So let me show you just some points along the spectrum of mutability, and hopefully, the first and the last will be obvious. Everything else along the way, yeah, who knows? So here is a mutable class. It's really, really obviously mutable. It's an automatically implemented property that's value, and it's got a getter and a setter, and strangely enough, you can write to the setter. And, I guess I should probably demonstrate that it's not write only. Okay, so yes, we can read it, we can write it, and that will print 30, whereas before it will print 20. So far, so obvious. If you're lost already, then heaven help you for the rest of the talk. I have no doubt you'll be a great developer sometime, but this talk may not be fun. Right, so that was a purely mutable class. Here's one that's shallowly immutable. So we have a value property, and if you haven't used C#6, this is still an automatically implemented property, but it's only got a getter, so it's a read-only field under the hood. And then we have another read-only property of type string builder. And as I'm sure you're aware, string builder is mutable. And the other very common example of this sort of shallow immutability would be list of T. So, you create a person object, and that person object has a list of friends. And you can't change what the list is, but you can change what's in that list. So we show an example here. We create a shallow immutable, we append to it, we observe state, we then do something, anything with it, and we observed a difference in state. Okay, so do you know, it's only just occurred to me, I've assumed that you've come to this having some idea what immutable and mutable mean. Hands up if you're really baffled by now because you came here thinking, well, I'd like to learn something about mutable and immutable, I have no idea what they mean. Okay, I'm going to keep going with that assumption then, that you have at least some idea. So, there's clearly mutation happening because we can see a change in state. Okay, next up, Popsicle Immutability. This is not an official term, but this was coined by Eric Lippert, who is a smarter person than I am by a long, long way, and so I thought I'd go with the flow. So here we have, it's much more complicated than our previous things, even though it's really only tackling one bit of interesting state. So we still have an int, and the idea is you can set this int to something, we could set it to something else. You can mutate it as much as you like until you freeze it. After you've frozen it, you can't change it again. The compiler lets you, but the type itself stops you from doing so. I should point out this is a bad implementation of Popsicle Immutability in that it's not thread safe. It's entirely feasible that actually we could observe a value other than 15. In fact, we could observe 15 there, and we probably observe 15 there, but even after we've frozen it, there may be some strange memory model madness that means we observe a change in value that another thread was writing at kind of the same time that we were freezing. In fact, I'll just do the one, memory model madness. We'll talk a little bit about that later on. So, aside from the memory model side of things, Popsicle Immutability has some upsides. You know, it's easy to use. I can use setters like this. More importantly, I can use object initializers. Value equals 20. I really like object initializers for mutable types. But the bad side is our type system no longer tells us what we want to know, which is, can I change this, and can I rely on no one else changing this? Okay? If you've got an immutable type, then you know what you can't do with it, and you know no one else can do anything with it either. Which reminds me of another kind of immutability I can't be bothered to write just now. So that's Popsicle Immutability. You know, if you have a method parameter, a constructor parameter of type Popsicle here, what are you going to do? And you want to store it in a field. Are you going to clone it or not? We'll come back to why that's an important choice and why immutability makes that an easy choice later on. Let's look at observably immutable. So, this is, again, it's not too long. So, we have a wrapper around a string, a name. And the name property itself cannot be changed. And string is immutable in C#. But we have this other field, cached hash. And that's not read-only. Badness. It's not used in any of the code on here, but when we call getHashCode, if cached hash is 0, we set it to getHashCode of name. So, hands up if you would deem this class to be immutable. Interesting. But many of you thought that Java's string class was immutable. String does this. I don't think the C# one does, but it could. There's nothing I can do as an outside observer to observe a change in state. So as far as I'm concerned, no one else can do anything to change its state afterwards. And it would have to tell me, okay, you may know that there's some mutable state, but I'm not going to let you see it. I view this as immutable. You need to be careful with it. Again, because of the memory model, it's quite nice that cached hash is an int. If this were a long, then this code would be bad in various different ways, because there could be multiple threads calling it, and stuff could see things happening in different bits. But here we know that we will set cached hash, and we'll definitely read back the same value. All is good. So we're getting more immutable. Here's some code that, if I hadn't put in the title unsealed, semi-immutable, you might have had to think a little bit to say, well, what's the difference between this class and the one that's obviously immutable later on? And the difference is this is unsealed. There's nothing in an instance of just unsealed semi-immutable that I can change. But that doesn't mean that I can regard it as an immutable type, in that if I have a reference to an instance of this class, the observable state of that object may still change. I can't observe any of those state changes just with what I've got. Well, maybe. I'll show you to string in a minute. But somebody else might be able to by virtue of a derived class. So here we have a class derived from unsealed semi-immutable. I'm actually going to just add an override of the string, and that's just going to return other value dot to string. So suppose, let's get rid of this. I can have, is this nice? Is this immutable? Is naughty. And let's make that unsealed semi-immutable. Okay. So I would like, if unsealed semi-immutable were genuinely immutable, I should be able to do console.writeLine, is this immutable, twice, and get the same result each time. But in fact, if I change other value, do I set it to anything? This is what tells me that I'm at least not dealing with an immutable object, which means that the object type must be also mutable, and just because I'm referring to it via something that looks immutable doesn't mean it really is. So if that's bad, what about this? It's not the example I thought. We'll come on to that one next. So this was one that I added just last week, in fact. This is what you used to have to do with C#5, okay, and earlier, back to C#2 or 3. So before we had proper, decent, automatically implemented read-only properties, and I wish there were a shorter way of expressing that. No, I don't want a new version of Java. Thank you. Nor do I want to give feedback on SQL Server 2016. So we have a private setter for this value, so that looks like it's publicly immutable. And this feels very close to the observably immutable bit before. But people, including me, used to use this for something that wasn't meant to be even privately mutable. It's just that it was the simplest way to make something that was observably immutable. So you put something saying, it's immutable, nothing's going to change all this privately immutable state, and then you have a bug, and you fix the bug by saying, I don't need to read the comments. Comments are for wimps. Comments are for people who want their code to work. Yeah. So in a properly immutable type, this wouldn't compile. If the type system is saying, nope, you're not allowed to change this, then all is well. So that's one area where the type system doesn't protect you from yourself. So I really need to reorder these examples a little. Let's give another example of the unsealed case, where it's actually okay, so long as you're careful. So the previous example was fine if you're careful and you never update value. So long as everyone reads the comment saying, don't change this property, that's fine. Similarly here, we have an unsealed class. Look, it doesn't say sealed, but it only has a private constructor. And I think I could even make this abstract. So, how can it possibly make sense to have an abstract class with a private constructor? Nothing else can use the private constructor, right? Well, code that is declared within the same program text as this class can access that private constructor. And that includes nested classes that are derived from the base class. So this foo is a new derived one, and so is bar, and so is baz. And each of them has their own little bit of state. In fact, derived one doesn't even have any state. Derived two has some other state, but it's immutable. So here we know, by looking just at the program text of this file, that this type is immutable. Because although it's unsealed, all of its derived types are immutable, and no one else can add any other derived types. Strictly speaking, in C#5, you could derive another type from this and have two constructors which each chain to the other. There's no sensible way of doing that, and to get an instance out of that, you need to throw an exception during one of those bouncing constructors, and then resurrect the instance during the finalizer, and evilness, basically. It's feasible because I've done it, but in C#6, it's been fixed, and it would be invalid code. It's a bunch of code I've commented out in the Abusing C# talk. And this is a surprisingly nice pattern, actually. I thoroughly recommend this pattern. It sort of mimics the Java enum pattern. So you would often have abstract methods in here that are overridden, effectively implemented in the derived class. So you could have a binary arithmetic operation that takes two doubles and returns one, and you have four instances, one for multiplication, one for addition, etc. And it's genuinely immutable. And the simplest genuinely immutable thing is just this. We have a sealed class. All its properties are read-only, and the underlying fields are read-only. And the type of every field is also an immutable type. If you can check those boxes, your type is immutable. Simple as that. Yay. Okay, so that's the sort of spectrum of mutability. Why on earth would we do this to start with? Java again. Anyone who's used Java, kind of any time since 1.0, so any time in the last 22 years. Name an API you really don't like that comes to the top of your head really quickly. Date, thank you. Oh, I was hoping no one would go, document factory or something. It's like, no. Java util date. I have a love-hate relationship with Java util date. I hate it because it's so appalling. I love it because if you want to give anti-patterns, you only ever need to reach to Java util date because it has them all. Well, Java util date and Java util calendar. A pair of classes that are so hard to use correctly, they're terrible. Date should clearly be immutable. And so if you're writing a person type and you want to accept their date of birth, you accept it as a date, which doesn't mean date, it means an instant in time. It's timestamp, effectively. Who'd have thought that calling a timestamp date would be confusing? But what do? You could clone it, or you could not clone it. So, do you write this.date equals date, or do you write this.date equals date.clone, or new date, date.getTime, or something like that? Well, how much do you trust the code that's calling you? That's what it really comes down to. And that's when you're accepting something. What about if you're giving it out? How much do you trust the code that you're giving something out to? Maybe your person constructor validates that the person is not more than 300 years old. Great. And maybe I'll dutifully clone my date when I get it, and then someone calls get birthday, or get birth date, and we return them the date. Do I trust them not to mutate it? If they mutate it, my validation earlier was completely pointless, because they can make this person be born 1,000 years ago. That's not good. They may not be able to change, they can't change the value of the field, but they can change the data within the object that that field's value refers to. I think I got that right. So these are sort of two examples, and a lot of other things come down to these two examples, but it's really about, do I trust other code not to change things? And even if I do, how hard is it to remember that I'm trusting them at every single step of the way? Fundamentally, your code is harder to reason about with mutable data. So you'll hear various benefits around thread safety. Immutable types are thread safe because if nothing, thread unsafety is all about different threads updating or reading data at different times and seeing or not seeing changes in state. So if none of the state changes, all is well. So immutable types are great for thread safety. I completely agree. Immutable types are good for performance because we can share all the data, we never need to clone it, so we don't end up with loads of copies. My guess is that most of the time, when you take defensive copies of mutable data in your code, that mutable data is never changed. So this copy that you've kept pristinely is pointless. It's for your own peace of mind. It's just in case someone changes it. It's insurance. But it never actually changes. So you sort of want copy on write semantics, which C# certainly doesn't have as part of the language at all. So this efficiency side of things, there are other times where immutable data structures are less efficient because you really want to change some state and you don't want to have to create another version of something that's that one with a couple of changes. But it can lead to more efficiency. It can definitely lead to thread safety. But the main reason to love immutability is I can see my code, I can understand my code. I come back to my current work. So I'm doing work involving an RPC API. And we have various settings. When you make an RPC, we want to know, how many times should we retry if it gets an error? What should the timeouts be? All kinds of complicated settings. Great. If I make them mutable, it's really easy to construct those settings. But then I need to think, do I need to clone them every time? And I look at the code and I just don't know what I'm going to do. And that happens every time I use them. Every time I pass them in somewhere, oh, is that thing going to change it? Is it going to clone it? Every time I receive it, is that a clone? Is it? Yeah. It's awful. Which is why last week we made them immutable, after all, for settings. Things that you don't really need to muck around with a lot. And all the code becomes simpler. So these are all the benefits. So why don't we just use them everywhere? Let's have a look at what C# has done over time. So, to start with, since day one, we've had value types, or at least since I started looking at it in the betas. We've had custom value types. Already a step up over Java. Now, admittedly, value types and immutability are an interesting relationship, which 26 minutes past 3 already, I doubt that I'm going to have time to come back to. But it's interesting. We have string and string builder, yay, so much like Java, that's all good. We have types being unsealed by default, which is somewhat tangentially related to immutability, but is a bad thing. Even though methods are non-virtual by default, yay, unfortunately classes are sealed. And back in C#1, a long, long time ago, how many of you used C#1, so before we got to C#2? Oh, there is a smattering, that's good. I don't feel quite as old as I did yesterday morning, ironically. You could only have public string foo. You could give it just a getter or just a setter, but if it had a getter and a setter, then both were public, or both were internal, or both were private. You couldn't have public getter and private setter, which is by far the most common combination for non-just the same. Crazy. C#2 came along with private setters and with automatically implemented properties. Hooray! A load of code goes away. Ironically, there are still people posting questions on Stack Overflow saying, here's my sample code, and I have 5 properties, and each of them takes 6 lines to declare, because I haven't learnt about the 11-year-old syntax for automatically implemented properties. And my guess is that plenty of them didn't start using C# until a couple of years ago. Automatically implemented properties rock for trivial things, which these almost always are. Okay, C#3, coming along, starting to enter the modern era now, has anonymous types. Yay, they're immutable. Well, they're shallowly immutable by default. Not only are they shallowly immutable, they come with a nice equality and get hashcode implementation. Yay, they come with toString. It's all goodness. So long as you don't have an anonymous type where one of the properties is a string builder or something like that, yeah, you can absolutely pass those around and know that they're immutable. Rock on. We have link. This is encouraging functional thinking, which is, related to immutability. They're clearly not the same thing. But we got the idea of, instead of calling list.sort, which clearly mutates the list, there's no concept of sort this list and, okay, you can't actually change anything, so, better hope it was sorted to start with. Instead, we have order by, which is take this arbitrary sequence and give it to me in an ordered format. Ordered order. You don't need to mutate anything, you just yield the new version. Likewise, select, where, everything. So we got to grips with the idea of transformations. Unfortunately, at the same time, we got object and collection initializers, which are fundamentally pointless on immutable types. Or at least, the way they're implemented at the moment, they're pointless on immutable types. You cannot create, you cannot use an object initializer for an immutable type. Okay, in C#4, back in 2010, we got optional parameters named arguments, which means that if you have a constructor that takes all of the data within your object, so 5 different values, you can set it just as easily and readably, most importantly, as you can with object initializers. So I love object initializers for they are a concise way of readably initializing an object. Let me just show you just in pseudocode the difference. So if I call new foo, in fact, new message box, X, Y, I can't tell what that means. if I know that this message box has a message and a title, if I call title equals X, message equals Y, that's much more readable. When I say readable here, I mean in terms of the code, not in terms of readable, writable. So that's mutable. So here we could instead have new message box title X message Y. Readable and may be immutable. So this is goodness. If you can get around the issues of versioning and these things, then it's good. If you add another property later on, then you need to add an overload. And if you start using optional parameters, then you have problems, because if you have two constructors, each with some optional parameters which aren't being filled in by the caller, then you can't tell the difference between them necessarily. So there are versioning issues, and that's where life becomes a lot harder. Have you noticed how very, very few of the patterns and practices tend to tell you about, right, well, the problem with this pattern is it's really hard to do version n.1. I think we tend to be good at sort of a couple of dimensions of thinking about code, but the time dimension's really, really hard. Particularly all the different ways in which you can have compatibility and incompatibility. So C#4 helped in certain situations, yes. C#5 did absolutely nothing. I mean, aside from the async, and aside from changing the for each closure semantics, and aside from caller line info and whatever, aside from all of those, what's C#5 ever done for us? Obviously, I love it. Async is awesome. So C#6. Yay! We have read-only automatically implemented properties, hooray! Which we could have told since 2002 would be really useful, but we only got them in 2015. Fine. I shall save ranting for another time, but fundamentally it's a good thing. We can initialize automatically implemented properties with default values, whether they're read-only or not. And this is useful for shallow immutable types, where you want to initialize something with a list of T. So our person with friends, you can get the list of friends and add to it, and it's shallow immutable. That has benefits in itself, even though it's not fully immutable. Okay, great. And we have, as I mentioned yesterday, expression body members make you feel better. They don't actually make your code more functional at all, but they may encourage you to use more functional constructs. So that's the sort of what changes we've had in the language. But let's have a look at what things look like in practice at the moment. So I've only gone as far as C#6. C#7 looks like it's going to have, well, there's tuples that are mutable. Looks like it's not having the immutability that I expected it to have. We'll look at the very end at something that may or may not be in C#8 and almost certainly won't be with the syntax that I've got. But fine. Let's think about some concrete examples of what you can do today. So we have a data model. We'll have a person class, a name, which is a string, an address, which is one of these, a list of phone numbers, or a collection of phone numbers. Each phone number I'm going to represent as a string, and a type which is sort of home, mobile, or work. The details of what type you should use to represent a phone number are beyond the scope of this talk. When I was in Malmö last Saturday, I got cheers for saying, we'll have it as a string rather than int, because that would be crazy. And then afterward, and that got cheers. And someone afterwards said, no, you should really use E164 format. There's this library over here. And I looked, and you know what the library uses? It uses my previous version of protocol buffers. So it would be immutable, but if I generated the same thing today, it would be mutable. The world is mad. So we're going to have a look at several ways of doing the builder pattern and see what we can do with what we call withers. So builder pattern, in a nutshell, is you have an immutable type and a mutable builder type. So in order to construct an instance of the immutable type, you first construct an instance of the builder type, mutate it however you want, and then call build. Boom. You don't have to implement it with any of the ways I've done here. I quite like the idea of having a builder class nested within the immutable class. I make my builders sealed as well, typically. There you can get really weird things where you've got a builder hierarchy and an immutable type hierarchy where you've made sure that the only derived types are the ones that you know about, so they are immutable, but it gets crazy quite quickly. I'd advise you to avoid inheritance when it comes to immutability entirely, other than the one pattern I showed you earlier on. So, let's have a look. Our public sealed class has two properties. They are both, we'll assume that phone number, in fact I've gone straight for phone number, let's go for person to start with. Right, so these are the only state of a person, and I trust that string is immutable. I trust that address is, because we'll look at it in a minute. I trust that immutable list is immutable, and that phone number is immutable. If you have an immutable list of string builder, you're still mutable, basically. Same reason as the shallow immutability earlier on, but sort of one level removed. This immutable list is just from the system collections immutable repository NuGet package. It's the plain one that comes out of the box. So this has a private constructor taking a builder, and then it reaches into the builder and grabs out the name, address, and converts the list of phone numbers to an immutable list. And the builder looks very much like the top level one, except it's mutable. It's only mutable in terms of the name and address properties have setters. The phones doesn't. It's one of these shallow immutable, I've initialized it already, etc. But this means that this is quite friendly to work with. All the other types, address and phone number, work the same way. And I can do this. So setting my name is easy. Setting the address is, well, it's not too bad. I mean, let me format it slightly more readably for a small screen. So I need to call the new address.builder, and I need to call build afterwards. And I need to do the same thing. Well, for the phone numbers, I only need to call the builder and call build. I don't need to put a .build on the end of phones because I'm only adding to the collection. And I could clear the collection if I wanted. And then I need to do a build after the end. So the bad news is I've got, let me format this appropriately so that we can see all 4 calls to builder.build for the various different builders. And basically, showing someone this code instead of what we would like, which would be new person. So this won't compile. There will be red squigglies. Just ignore them. Name equals John. Address equals new address. City equals Reading. Street equals C. Phones equals, and then, yeah, we're having a construction initializer. New phone number type equals phone number type dot. Okay, so, and let's make it actually representative and have 2 phone numbers. So in terms of which code you would like to see, does everyone agree that this is less crufty than this? And the difference is really only .builder, 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 build, 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 build. 4 occurrences of the .builder and build. This is what convinced everyone that protobuf 3 should be mutable, despite the other engineering trade-offs. Okay, so that's the first builder pattern and how you use it. Second builder pattern is freezable. So this, if I look at the program to construct it, it looks exactly the same. I mean, I haven't got any phone numbers here, but it's exactly the same. And actually, I need to call .build on the end. You could have an implicit conversion from the builder to the non-builder type. I would advise against that, partly because then this var would be the builder. There'd be a difference between that and that. And I don't think that's a nice difference. This feels right. Okay, but the important part internally is this is a slightly more efficient version. So you'll see we have the dreaded private setters. And the reason is we actually build this up one property at a time because our builder, previous builder type, had 3 properties, separate state, and then we copy that state into a person. This builder type has a reference to that person, and you say, oh, you want to set the name? Okay, I'll set the name behind the scenes. And the idea is that we never let this person that's sort of still under construction, we never expose that to the outside world as a person until we know that nothing else will change it. So here our name property just delegates to underlying.name. Likewise here. And then when we call build, we freeze our list of phone numbers. So we've got Popsicle Immutability. It's all about observable immutability here. So we freeze our list of phone numbers. And then really, really importantly, we say underlying equals null. And the underlying property as opposed to field says, you know what, if we don't have an underlying person yet, we'll just construct one. So you can construct a builder, call build, and then start populating another one. It's not terribly clean API-wise, but it can work. And this will quite possibly fail in terms of memory models. If something manages to get the reference to, just because I'm returning here, and I've already set underlying to null here, well, maybe something is going to 2 threads having references to the same builder. You call build in one thread, it says, yep, here's your underlying person object. Meantime, there's a setter over here that's cunningly changing the value of that person. This is not nice. Fixing it is far from trivial, at least without locking. With locking, it's probably not so bad. But my guess is that very few people using this pattern would use locking. And most of the time, that's going to be fine. The number of times you share a builder between threads, that's crazy. That's so crazy that string buffer in Java is entirely synchronized, and they realized, you know what? No one uses it needing the synchronization. Let's just give string builder instead that is unsynchronized, and if you decide to share a string builder between threads, then it's your own fault. Okay, so that's a sort of observably immutable builder. Our next one, right. So this is still the builder pattern, but it's in reverse. So normally, person is the immutable form, and you have a builder that's the mutable form. And you construct an immutable one from the builder. Well, here we still have a mutable one and an immutable one. They've just got different names and a different way round. In theory, it sort of doesn't make any difference. In theory. That's the same kind of theory that says it shouldn't matter that C# methods are non-virtual by default and in Java they're virtual by default. Because you can express the same semantics either way. But how often do you see people adding virtual to methods in C# for no reason? Or how often do you see people making methods final in Java? If you give two developers the same API to build, basically, they'll just use the defaults, because defaults matter. So, here, person, which is fundamentally what you're going to be passing around most of the time, is your mutable builder. And you can say, well, if I want an immutable form, I can create person.immutable. And that's fine, and you get all the benefits of immutability, except no one uses it. And then you decide, oh, well, I'll tell you what, I will have an interface. I will solve this by having an interface, iPerson, that both person and person.immutable implement, and it has the read parts of it. And then you try using that, and you say, I shall make my method accept iPerson, because I love inheritance and interfaces. It's all good. And then you receive your person and then think, okay, I've just had that as a constructor parameter. Is it immutable or not? Because if it's immutable, I can just save it to my field. If it's mutable, I should probably call the toImmutable thing first, or save a clone. And basically, you've lost all the benefits that you were trying to get at, but you've got more complicated code to get that lack of benefits. So it's a no-win kind of scenario. One more. Here we don't have a builder pattern at all. So we have a person class that is totally immutable. And you construct it by giving all the bits. And maybe you pass in null, who knows. But the main thing is, you're not stuck. When you've got one person, you can create a new person that's similar to that very easily. You can call with name, with address, or with phones. The naming here is important. So, if I don't have the address yet, I can create a person that's sort of half complete. Issue 1, validation. If you're allowed to have incomplete things, you can never really validate, and you can have a validate complete method, and given that it's immutable, at least it'll stay valid if it was valid. But it's a little bit smelly in terms of the type system. But I can fill it in later by saying john.withAddress and then pass in the address. The reason the name is important, you could have john.setAddress instead. That would be a bad thing to do, because with address is very obviously wrong if you just have john.withAddress. Boy, yeah, what about that fictional person, John, who's got an address over there? It's clearly wrong. This is one of the... I think every time I've given this talk, I've included this unscripted note, and I should really just put it in the agenda at some point, about why names matter. So, how many of you have either written or seen someone else write, string text equals foo, and I want to change it to fee, so I'll do text.replace O with E, and that looks okay. Likewise, date time flight equals datetime.now. Fortunately not, it's in time span dot from hours 3-ish, bit less than that. And that looks okay. It's not, because text.replace, as I'm sure you all know, that's not doing what we want it to. It's returning a new string of fee and doesn't change text at all. Likewise this, datetime is an immutable value type, as most value types should be. So add doesn't change anything. But that's bad, because add sounds like it does. Add is I add something to the table. I add it to... If I have list.add, that mutates things. If I had plus, or after replacing, not the best name I could come up with. And at the same point that I start to put this into the script, I will also try to think of a good name for this. But the reasons these are better names than replace and add is that as a statement in itself, text dot after replacing blah, 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 it leaves you wanting more. It leaves you wanting to do something with the result. And likewise, flight dot plus, well, that's a relation between, you know, flight plus thing. It sounds like an operator rather than a directive onto that's going to mutate the object itself. We're not very good at coming up with names that work like this, but I would strongly encourage you to do so. If you have immutable types that there are operations on that give another instance of either the same type or something else, I would strongly encourage you to give method names that are obviously not changing, because no one is going to read your documentation saying it's immutable, or very, very few. Statistically insignificant numbers of people read documentation. And frankly, statistically insignificant numbers of developers write decent documentation as well. And hands up, I'm exactly the same. Okay. I'm going to show you some craziness in the memory model just very quickly. I've got 10 minutes left. So Ted talked yesterday a little bit about the memory model. And the problem is that C# doesn't really have a memory model as such. It sort of delegates to the ECMA CLI memory model. But that's really, really weak. And if you don't believe that it's really, really weak, then let me show you some code that's not just a weakness of the ECMA memory model, but even the Microsoft .NET 2 memory model, which I believe is still in force as the documented version. And by documented, I mean Joe Duffy wrote a blog post. That's as close to documentation as I think we've got. Look at this method. Does that look safe to you? It looks safe to me. Theoretically, it's not. Okay, so if we have two threads, both executing this loop, so they're calling this supposedly safe method and passing in name. And that's all they're doing. And as they're switching around, they're setting the name to either null or ouch. So we would expect that this call would probably still see a null value and would return -1, and this call would probably still see an ouch value and return 8. So -1 or length times 2. And we know about memory models. We know that threading is difficult and that maybe the other thread has set name to ouch before, you know, after name equals null, maybe the other threads come in, said name equals ouch, and that will return 8. And that would be fine. Maybe it's set it, but we haven't read it yet in our thread. So we'll still get -1. That's fine. What isn't fine is it going bang. That would be unexpected. Well, says the JIT compiler, or rather the JIT compiler authors who are very keen on optimization. They say, well, the memory model says that unless there are volatile reads and writes going on, I will basically assume that mine is the only thread that exists. And by the way, for optimization purposes, I love to do inlining. So what happens if you inline this call? Well, do you know what? Let's make it easier by using C#6. This is now really easy to inline because we can just take the whole of that code and say, inline, as in get rid of that. And wherever we had X, we want to have name. And we'll do the same here. And I need to remember not to commit this file later on. Otherwise, next time I give this talk, it'll be nonsense. Right. Does that feel safe? No! That's not safe at all, because look, I'm testing whether name is null and doing one thing, and then if it's not null, I'm using the value again. And another thread could have changed it in between. So I would like to think that smart folks such as ourselves would say, no, that's not thread safe. I don't like that code. But the JIT optimizer can change our perfectly sane-looking code into this. If I hadn't said before that this doesn't really happen, I would expect you to be very, very scared by now. Either very scared or very confused. Either is fine, and if you're confused, it's my fault, not yours. But it's crazy stuff. And you can apply it to other situations as well. So this is the other example of a Commonality Check. So we all know that this is bad, right? Because click can change between the if check and the invocation of click. So we introduce a local variable. And then if that's non-null, then we use that. We don't use click more than once. Well, that's what you think, says the JIT optimizer, and cunningly just says, get rid of that local variable and just say if click not equal to null, then click. And I say, but I know C#6. I can make this smarter anyway. I can use click.invoke. And this time the compiler says, well, that's just equivalent to this one. And the JIT optimizer says, I can mess you up like crazy. Cue Ted going, the gods of computer science hate you. I can't really do that with them. This mic doesn't work for that. I don't think I've got the voice to say hate you in quite the same way anyway. But anyway, this should convince you that we need a better memory model for C#. I'm doing what I can, which is very little, but I'm trying to set up a working group of smarter people to provide something which is at least documented. So either we need a memory model that says, do you know what, this isn't safe, or we need a memory model that says, screw you, JIT optimizer, please don't mess with my code so much. Or at least, only mess with it as much as you already do, because it's okay. I'm going to skip most of the issues around immutability. Hopefully I've persuaded you, I have 3 minutes left, hopefully I've persuaded you that immutability is good for your code in terms of dealing with a value that you've been given. It sucks for creating that value in the first place. Okay, it makes that part harder, and that part's so important that sometimes we're willing to sacrifice everything else. We leave a comment saying, okay, this property returns a mutable value. Please do not change it. If you do, it's your own fault when everything else messes up. I've written a slightly different version of that comment several times recently. So hopefully, eventually, the language may catch up. In C#8, we may have record types. We may have withers. When I showed you the withers, John.withAddress, and you could chain them John.withAddress, .withName, .withPhones. That has a problem, which is if that's the way you build up your final object, you've left a breadcrumb trail. Note to self, never use that word again in a talk. You've left one of those littering the stage and the garbage collector with objects that no one cares about. The compiler can do smarter things. One of the record type proposals in C#8, which I have a non-compiling version of, will allow you to do with, let's modify several things at the same time, where modify is create a new version with these changes. And it can do it efficiently. This may be roughly what the code looks like. So these are address classes in some fictional version of C#8. And instead of, previously I had person that would be twice as long as this. This is all the entities. I've got an enum, but that's all for phone number type. This is all you would need to write. Unfortunately, this leads to all kinds of difficult design decisions. This class is sealed. Can I have a record type that's unsealed? If so, what does that mean? Can I add my own properties to this? Can I add my own methods to this? Who knows what I can do? I understand you're taking a photo. Don't expect it to look like this. It probably won't. If it happens at all. I think the C# design team are now so fed up with trying to get this right that they're saying, right, C#8, boom or bust. If we can't get it right in C#8, we're going to throw away the paper and give up. But it's nice. And this is possibly the kind of syntax we could end up with withers. So it becomes part of the language to say, well, this new record is that record with these modifications. So, in conclusion, immutability rocks, apart from when it doesn't. Use your brain, make choices, bear it in mind, don't use the anti-patterns of making immutability badly. The builder pattern is a perfectly fine one. I would recommend the dirt simple, just make the immutable thing obviously immutable and take the hit of a builder being, a copy that is then copied into a new object. I need to run, so I don't have any more time for questions, but thank you very much and goodbye.